So let's start. So this week I am going to talk about these two papers, and note that we are now embarking on a different topic, and it's called dynamic reachability. So reachability problems are basically extensions of, say, connectivity problems to directed graphs. So in an undirected graph, if a node u is reachable from V, it's also the other way around, that V is reachable from U. But in directed graphs, it might not be the case. So you want to maintain reachability information in directed graphs in a dynamic setting. And for some time now, for the next few weeks, we will be considering only this topic. Okay? So it's a new topic. And before stating the dynamic reachability problem, let us look at this problem in a static setting. Okay. So we will be considering three versions of this problem in increasing order of generality. So in the static setting, so this is static setting, okay, for the time being. The input is a directed graph, and now there are three problems. One is single source reachability, call this SSR, where you are given a source node S and you want to compute all the nodes that are reachable from S. S to V path. This is single source reachability. The second problem is called strongly connected components. And here you are just asked to return the strongly connected components. I will get back to this problem in a minute. And the last problem is called transitive closure or all pairs reachability. So here you would be asked to return the information about any pair of nodes. So the question is there an UV path in the graph where U and V are two nodes, any two nodes? Okay. So as I said, I will get back to this problem in a minute, but before, let us consider single source reachability and all pairs reachability. Quick question. So in the static setting, what is the best running time for single source reachability? Sorry? Yes, right. So it's O of m plus n, right? M is the number of edges, n is the number of nodes. Because you can just do a breadth first search or depth first search from this source node S, and you can get all the nodes that are reachable from this node. So, do BFS or DFS. From S. This is the static setting. All pairs reachability, you just need to return all the pairs that are reachable, all the UV pairs, so that there is an UV path. What will you do? Order of m times n, right? Do a BFS from each of these nodes as a source. And these are currently the best known running times. Just very simple, and for all pairs reachability, I think there exists something that uses fast matrix multiplication. But if you just look at combinatorial algorithms, nothing better than this is. Yes, right. That's what I said, right? It uses fast matrix multiplication, but if you just look at combinatorial algorithms, nothing better than this is known. Okay? And most of the time we will be concerned with combinatorial algorithms. So, we can just treat this to be the best known bound in the static setting. Now, what remains is strongly connected components.
Formal distinction. What do you mean we treat this as the best?
Sorry?
Lower bounds. We take these to be the.
Yes, in the sense that okay, there is no unconditional lower bound available, but no better algorithm is also known.
So what about that? Omega or whatever.
That uses fast matrix multiplication.
So how do you differentiate? I mean, is there some formal?
Oh, if there is a formal thing.
So like if the job is sparse, then this is the best.
Yeah, sure. No, I'm just asking, is there some formal definition of saying an algorithm is combinatorial and not?
No, okay, this is sufficiently formal, right? I mean, you just cannot use fast matrix multiplication as a subroutine. Now, you can say, ask me, yes, okay, maybe it can get a little bit more formal. It can be made a little bit more formal, but yes. Yes. Okay. Next, strongly connected components. How many of you know the definition of a strongly connected component? Okay. So, still I will just mention it in 1 minute so that we are on the same page. So, for SCC, you just look at this relation, you just define a relation and say that U is related to V for any two nodes if there exists an UV path in the G and simultaneously there exists a VU path in G. Then you can note that this is an equivalence relation. Meaning that this relation is symmetric. If U is related to V, V is also related to U, and this is transitive, meaning that if you have U related to V and V related to W, then it implies that U is related to W. So, this is transitivity. And this is symmetry. Now, you can show that this relation will define a partition on the node set. How will you get that partition? You just start with any arbitrary node V. Just look at all the nodes that are related to this guy. Okay? and so let us call them CV. Then you look at any other node, say V prime, that lies outside this set CV, and again look at all the nodes that are related to CV prime. And you can show that these two sets will not intersect, because if there was an element in this intersection, then by transitivity V will be related to V prime and V prime will belong to CV. So this way you can build a partition on the set of nodes. And what is nice about this partition is that if you look at any two nodes, say U and U prime, that belong to the same partition, then there is a path from U prime to U and from U to U prime, and all the nodes in these two paths lie in the same set. Okay? So this gives you the strongly connected components of the graph. Clear so far? So it's a generalization of connected components to directed graphs. So if you just look at one strongly connected component, it's a self-sufficient unit. You can think of it like that. I mean, every node, every pair of nodes within that components are reachable from each other via nodes in the same component. And the next thing to note is, I will use this thing called DAG. It stands for directed acyclic graphs. Every directed graph, any general directed graph, if you look at its strongly connected components, you can get a DAG out of it. How? Just look at these strongly connected components. Can there be edges between crossing these components? Can there be an edge like this? There can very well be edges like this, right? But the point is that if there is an edge going like this, there cannot be a reverse edge, because if there is a reverse edge, these two components will collapse. So basically the idea is, I am just going to write it down formally. Just look at the strongly connected components, and whenever you see an edge crossing these two components, just put it there. Okay. So treat these components as meta nodes, and there is an edge between these two meta nodes. If there is an edge between, say, U here and V here, that were the original nodes, and then just look at the resulting structure. That will be acyclic. There cannot be any cycle. Okay. So G is the given graph, right? So consider this new graph, G star. So what is C star of V? This is the collection of strongly connected component. And there is an edge, say from C to C prime, if and only if there is a node in C and a node in C prime such that there is an edge from U to E prime in the original graph. So this is the graph, and the claim is this graph G prime is a DAG. And the proof goes as follows. Suppose there is, so these are the nodes, okay. So there are T, say suppose there are T strongly connected components, and you can sort them in topological order. And now suppose you see a cycle. you go till say Ck, and there is an edge. Then if you take any two nodes, u in C1 and say v in Ck, there is an uv path. So you can show this, and also there is a vu path. So basically then u and v should belong to the same strongly connected component, which is a contradiction. Okay, so far so good. Sorry? Yes, yes. Okay. Now, so we need to keep this thing in mind. We will be using this thing multiple times while we are looking at dynamic reachability. Now, so far we have been considering the static setting, and we considered the best known algorithms for single source reachability and all pairs reachability. What is the best known static algorithm for strongly connected components? Order m plus n, right. Now, do you remember how to find that? How will this algorithm go? Okay, cool, good. Let me go through this in just 2 minutes so that everybody is in the same page. Look at this graph G star and sort these components, these meta nodes, in topological order. Okay. Now, you can define the sinks and sources in this graph G star. What is a sink? A sink is a node that has no outgoing edges in G star. A source is a node that has no incoming edges. Intuitive definition. So the idea is, so in this topological order, the last node will definitely be a sink, the first node will definitely be a source, and there can be more sources as well. Okay. Now, suppose somehow I tell you one node that belongs to a sink. Somehow magically I tell you. Then what you can do is as follows. So this is say Ct minus 1. You just run a BFS or DFS, whatever. From you. You will find all the nodes that are reachable from you. So you will find reachable set from you. So this is the guys such that there exists a UV path. What will be this set? This set will exactly be equal to CT. So you can show that this RU is going to be equal to CT. Why? Because of course it will hit all the nodes in CT, because by definition all the nodes in CT are reachable from U. And can you go to some other node that lies outside CT? No, because then this CT would not have been a sink. Clear?
We are finding the SSCs.
Yes. Strongly connected components.
How do you ensure? So there is a UV path. How do you ensure there is a VV path? Because that's a sink he's in.
It's a sink, right? CT is a sink. So I am just giving an outline of the algorithm. So the outline of the algorithm is CT is a sink. First, assume that somehow we are given a node in this sink. I will get back to it, how to get this node. Okay. then we can just run a BFS from U and recover all the nodes in this component, because the output of this BFS will coincide with the nodes in this component. You got this part, right? There will not be any edge going out of it. So then what you do? You can just remove all those nodes and edges and repeat. So then again take a node, say ut minus 1, that belongs to this sink in the remaining graph. Again recover this component ct minus 1 by doing this and repeat. And how much time will it take? I mean, barring this part, this finding this node in the sink, barring that part, it's taking you linear time, right? Because you are not probing any edge more than once. Okay. So now the crucial thing is how to find this node. I mean, just give me an algorithm that will find you some node that belongs to the sink. I'm going to get to that, but first let me just write down the outline of this part. The second step is identify BFS remove this component ck, repeat steps 1 to 3 till okay. Now, how to find this? How to do step 1? So the idea is, I cannot give you actually an algorithm for finding a node that belongs to the sink. I cannot. But what I can do is, I can give you an algorithm that will find a node that belongs to some source. And if that is the case, then what you can do? You can just reverse the direction of the edges, you will get the reverse graph, and run that algorithm on the reverse graph. Because in the reverse graph, a source will be a sink in the original graph. Okay? So, let's look at the reverse graph. I'm just writing. With respect to the original graph, what H set E, everything else remains the same. And how will you do that? Just run a DFS on the entire graph. Then do a post order traversal and look at the node that you reach last in this post order traversal, and I claim that that node will be the desired one. So, for doing this, what you do? Run DFS on GR, do a post order traversal, and finally return the node V with maximum post number. And why is it the case?
Basically keep an array of the post numbers and then keep on
Yes.
returning the maximum.
Yes, that is it. And why is it the case? Because you just look at the node where you started your DFS from. Say this node was here, okay? Let's look at any CK and say this was U, and you started your DFS from U. Then you will never recover these nodes when you do the DFS from U, right? Because you cannot get back here, right? So you will recover all these nodes, then probably some nodes in some other components there, and then it will stop because you cannot find any more nodes that are reachable from you. Then you will have to pick another node here because you have not exhausted all the nodes in the entire graph, and it will go on. And in the end, you will have to stop at its source. That is the main idea. You can just work it out, it's not difficult.
Instead of saying doing a post order, we can say the node with the last finish time of DFS.
Yes, the same thing, the last finish time of the DFS. It's the same thing. So you can work out the details, but this is the algorithm. And now, what is its running time? This part just takes O of m plus n time, right? So what is the running time of this? Step 1 will take O of m plus n time. Step 2 again O of m plus n time. Step 3 again linear time. Now step 4 repeat. How many times will you have to repeat? At most n times, right? Because each time you repeat, you are removing at least one node. So the total runtime so I am going to assume that m is greater than or equal to n, otherwise the graph is not connected and it's okay. Sorry?
Can be made into
Oh, sorry. What I said, it was wrong. No. Sorry. It was wrong. Silly mistake. This, for doing this, what you do is you just run this algorithm in the beginning. Just calculate all the post numbers. You don't have to run it again. So the idea is, that was a silly mistake, I should not have said this thing. The idea is this. So given any node Ck, any meta node Ck, let us define this number, say Wk. What is WK? You just look at all the nodes in CK and look at their post number. Take the maximum post number. Okay. What I just showed you was the argument that we went through. It says if you just sort these nodes in decreasing order of WK values, then you will get a topological ordering of this graph on the meta nodes. Did you get what I mean? So W1 will be greater than W2, this will be greater, and so on. In G it will be the other way around, so this is GR. No. So the idea is, so this is GR, right? Can't you see that W1 will definitely be greater than WT?
These W's are
The exit times.
in G or GR?
In GR. This is GR, as I said, this is GR. So why is this? Because suppose your source node, where you started the DFS from.
That is your source.
Yes, suppose your source node was here.
I thought that was this.
No. Okay.
Source
Sorry. I'm not talking about the source node as in here. I mean, okay, this is the GR graph. Fine.
The first node which we started.
Yes. The first node where we start the DFS from.
Second DFS.
Okay.
The difference, but here we are talking about
We are not even going there first. We are only looking here. Right?
Yes.
Here is the first node.
Yeah.
This is just a graph. Okay. Forget about whether this is G or GR. This is just a graph. Now what?
We want to find the source node. Actually, we are going to find the ordering so that whenever we remove the maximum will be the source
Yes.
of the remaining.
Yes. That is the idea. So this is just a graph. What we want is a topological ordering on the graph defined by the meta nodes. How are we going to find that? The claim is just do a DFS.
For the complete graph.
This is not true.
Sorry.
This is not true. I mean, if I have two sources,
Mm-hmm.
my suppose C1 and C2 are sources,
Mm-hmm.
then W2 might be greater than W1. It depends on the ordering. This is a partial order in which every chain is.
Yes. That's what I said. That
But this in generality doesn't hold.
no.
You can't say W1 is greater than W2.
No, it will depend on the DFS, right?
See, if there is no edge from C1 to C2, then you
No,
don't have-
I understand, but my point was different. My point is that you are getting this order after looking at these numbers, WK.
Okay. This is in G or GR?
This is in GR.
This is in G. Okay.
No. Okay, what I said was how to get a linear time algorithm. Just look at GR. Just do this DFS. Okay?
You do the DFS to get the whole graph. When you haven't visited everything,
Yes.
take another one, do a complete DFS.
Yes.
Get a forest.
Yes. Okay, let me just say something else. Do DFS on GR, okay? Then just define these quantities, WV. This is the post number of any node V, okay? Now step 1, identify. Now here it's the original graph, okay? And you just need to implement step 1. How will you implement step 1? Identify some node that belongs to the sink. You just say let V be the node with maximum post number. Okay, and now that will give you this CK, and let V belongs to CK. You do not know which one is CK, okay? Then you identify the nodes in CK by doing this BFS, remove the edges in CK, and then in the remaining graph again let V be the node with maximum post number. This will give you the total running time of O of m plus n.
So you're basically finding a sink in G and not a source in G.
It's the same thing, right?
So it's a source in GR, which is a sink in G.
Yes.
See, okay, the post number is like this, okay? So if you start with a vertex into the BFS, that vertex gets 1.
No,
Okay,
that
that's
graph gets the last
finishing-
number.
The finishing.
Yes,
Okay.
that's I said. Post order traversal.
No, that vertex may not get the maximum thing. I mean, the vertex which you start from at the end and then you finish at
Yes.
the end, that vertex will get.
All I said was, okay, what I meant was if you just start from a node, it will get a larger post number than any of its descendants. Then you exhaust all of its descendants, and if there are some more nodes left, you start from some other remaining node.
Then the old
Yes.
tree will get a larger post number.
But than the previous one. Yes.
And one more thing, why is it strongly connected, this thing? Because you found a sink vertex, you find a vertex which was in the sink, and then you do BFS from
BFS or DFS, it does not matter. Okay. So this is a sink in GR. So now this is GR. Don't get confused. This is no, sorry, this is G. This is G, and this guy is a sink.
You found all the vertices which are reachable from V, right?
Yes, you have found all the vertices which are reachable from V. So of course you will cover CK, no doubt, right?
But for CK to be a strongly connected component, we also want that each of them should be, there should be path from those vertices to V as well.
No, so here is the thing. This guy has the property, since this is sink, that if there is a V to U path, then there must be a U to V path. Suppose it is not the case. So there is a node U such that there is a V to U path, but there does not exist a U to V path.
There are different SCCs, because V is not in a sink SCC.
Then where will this U belong? This U will be somewhere here, right? And how can there be a V to U path? There must be an edge crossing these two. Then CK is no longer a sink. Okay?
We are starting with a strongly connected graph.
No, this G is not as strongly connected. We are just recovering one strongly connected component.
Then it might be the case that in G itself there was no U to V path. Suppose in G itself there was a V to U path, but there was no U to V path.
Then we are getting a contradiction. Don't you see that? Because, okay, CK is a sink in G. Understand the definition of sink, right? So CK, you just look at the strongly connected components, look at their topological order.
CK is a sink in G star.
Yes, CK is a sink in G star.
G star is G not the equivalence relation.
And there will be a sink. So we don't know what a sink is, but we know there is a sink. And suppose we know a vertex which is in the sink, we can get the sink. That is what we say. So assume V is in the sink and get the whole thing.
CK is a sink in the meta graph which we are taking.
Yes.
So which means that from any vertex inside CK there cannot be any edge which goes to outside CK.
Yes.
Which means that from a vertex in CK if there is an edge to another vertex,
It should
then
be
that vertex should be in CK. So there is a path from that vertex back to
See, all I'm saying is, what if there was no U to V path in G?
Then your answer is then CK is not a sink.
there cannot be.
No, then it's just a singleton. It's not a connected component, it's just a singleton. That's
I
all.
don't get it. So why is it not a sink there?
Suppose you are saying that there exists a node U such that these two conditions hold.
V to U is a path, but U to V is not a path.
Okay. Such that,
V is not a
but there is no U to V path, okay? Where is this U? It belongs to some strongly connected component. Where will that U belong to? Somewhere here. What is this? This is the topological ordering of the meta graph. U is here. Okay. Now what is this V to U path? You just chart out this path from V to U. It will stay somewhere here, but at some point of time it needs to get out. And the point it gets out of CK, how can CK be a sink then? Because there is an outgoing edge from CK. Okay? Okay. So my whole idea in going through this was, I mean, it's good to have a feel for the static problem before we move on to the dynamic setting. Okay. Now, let me erase this part. Now we will move on to the dynamic setting. So, in the dynamic reachability literature, if you just look at the updates, we will mainly be concerned with decremental setting and fully dynamic setting. So, in decremental setting, the update is simply delete an edge. In the fully dynamic setting, the update is either insert or delete an edge. What are the queries? It depends on the problem, right? So, for single source reachability with source node S, the query will be is there an SV path where V is some other node V is some other node. In strongly connected components problem, the query will be are two nodes U and V in the same strongly connected component. And finally, in all pairs reachability, the query will be is there a UV path where U and V are any pair of nodes.
So, in the first case, the S is fixed from
Yes, S is fixed.
whereas will be only be some V.
Yes. And as we said, in the next few weeks, we will be considering both decremental and fully dynamic setting. But for this week, we will just take up the decremental reachability problem. So in today's and tomorrow's lectures, we will show, or at least try to finish these results. For single source reachability, we will get this is the total time, meaning you start with a graph of m edges, then you delete those edges one after another. What is the total time you spend? So it means update time, amortized update time is O of n, right? Because you are going to delete n edges. For strongly connected component, oh, it should be SCC. Why am I writing SSC? This is strongly connected component. Yes. We will again get the same total update time, total time. This is also total time.
But what will be the query then?
Yes, I am coming.
Queries will come in between updates. Right?
Yes, queries will come in between updates. I am just going to come to that. Okay. And for all pairs reachability,
This total time is total update time.
total update time. So as I said, amortized update time is you just divide the total update time by n, by m. Okay. And for all pairs reachability, we will also get the same total update time. And for each of these results, the query time will be worst case O of 1. Okay. So now note that in a decremental setting, we cannot hope to beat the static algorithms, right? So this is optimal. Why? Because if you got little o of mn time in the decremental setting, then of course you can get little of mm time in the static setting, and that will be a groundbreaking result. So I should add a qualification here. It's not optimal. I mean, optimal under the assumption that there is no combinatorial little o of mn time algorithm for static all pairs reachability. Okay. But for these two things, it's not clear. I mean, maybe there is something better or not, but who knows. Okay, so this is the roadmap. And now let me point out this first paper, Even and Shiloh. This will give you this update time for single source reachability. And for strongly connected components and all pairs reachability, you need to look at the second paper. Okay, so I think maybe today we will just deal with the first paper, even Shiloh trees. So, this data structure itself is called event Shiloh trees, and it's used in many different dynamic problems. It's a very primitive data structure. Okay. And it's basically what it is doing is it's doing decremental breadth first search. Now, decremental breadth-first search. So, note that for single source reachability, you don't need to really maintain the breadth-first search tree. It's giving you something stronger, right? The breadth-first search tree is also the shortest path tree. But the eventual tree is actually going to maintain the BFS tree under edge deletions, and hence the title of the paper is also an online edge deletion problem. Okay. So, S is the source, this is going to remain fixed, and since we are just maintaining a BFS tree, let us start. Okay, let me just take a step back. Right now what I am saying is I am just trying to highlight the main idea. Later on I will give you the complete pseudocode for this. So, do not take it as the complete picture. Okay. So, we want to maintain a BFS tree in a decremental setting. The most natural thing is to start with any arbitrary BFS tree. So, we have a BFS tree, and so now suppose this is layer I. And this is layer 0. And now suppose here was this edge UV. So, V was in layer I plus 1. Okay, first, what is the query? The query is and let us just denote this tree by TS. This is this BFS tree. Okay, what is the query? Delete UV from the graph. To address this query, what is the easy case? Exactly. Does not belong to this tree. Why this is easy? This is a trivial one-time update. Right? Do nothing. You are only maintaining the BFS tree. So, the hard case. For the rest of the time, we are only going to talk about the hard case. UV is a tree edge. Now, a tree edge will always look like this, that U belongs to some layer I and V belongs to layer I plus 1. Right? It cannot be the other way around. I mean, if the parent belongs to layer I, the child will belong to layer I plus 1. Okay. Now, let us try to work it out ourselves. UV gets deleted. And let us just look at this structure. There is also a subtree rooted at V, and each of these guys also have their own subtrees. So, note that only this subtree of V gets affected due to this deletion. every other part of this whole entire BFS tree, you can just leave them untouched. So how will you try to fix it? Any suggestion?
First, check if there's a U prime in layer I which has the edge to B.
Good. You see what he meant? He meant was if there is an U prime that is in same layer as U, and you could find an edge from U prime to V, then what will happen? You can just add this edge. And then do you need to change anything? No. Why not? How can you be sure that this is the correct BFS tree? But we are maintaining a BFS tree, remember, it's not reachability. So the argument is if you delete an edge, the distances of the nodes can only increase. No doubt, right? And these layers are the distances. Layer of a node, it is distance from the source. So you have deleted an edge, but I have given you a new BFS tree where this layer of every node remains the same. A new tree, a reachability tree, where the distance of every node remains the same. So it has to be a correct BFS tree. It has to be a shortest path tree. So this is a mildly easy case. You can find this. Otherwise, what is the hard case? There is no such edge from V to V from some node in layer I. So you now notice that all the incoming edges from V, they are either coming from layer I plus 1 or they are coming from below, or they might come even from here. I mean, who knows? Okay.
So we can check all nodes which are not in the sub.
You can
Check all incoming edges. So like we do it for layer I plus 1 and layer I plus 2. So
Okay, so you are saying, okay, first now check layer I plus 1. Is there an incoming edge from layer I plus 1? So you can see what the difficulty is here, right? What is the difficulty? Suppose we don't have to go too far down. Suppose there is an edge to V from some other node U prime, which is in layer I plus 1. Can we add this edge?
You should do something. You should look at the children of D and see if they have it.
no, but this will be a very
But this won't affect.
because it's like it's just I plus 1.
No. That is the point. That is the crucial point. We can surely add this edge. The distance to V is correct because you cannot find a distance I path. But what about V's children? I mean, there is this guy W, say. And yes, this guy was, say, at layer I plus 2 now, okay? Initially, this guy W was in layer I plus 2. The moment you add U prime to V, W's layer becomes I plus 3. But is that a correct layer? You never know, right? It might still be I plus 2. I mean, there might be, W might have,
So even W
yes.
is able to use
Yes, or U prime or something here, I mean, okay, U double prime in layer I plus 1. So in this case, you no longer leave this subtree untouched. You have to fix it. And potentially you have to fix every node in this subtree. It's going to cost you a lot.
No, you have to just fix the change.
If one child does not have an edge from D plus 1 to it, its children might have an edge from I plus 1.
Yes.
You have to
The
go
more,
You might have to do that.
Yes, you can potentially have to go down the whole thing because this is just a cascading effect. I mean, maybe you did not find it a parent for W, but then you look at W's child. The same thing can happen again. Okay? So this is the hard part.
what is all we are storing? We are only storing the TS or we are storing whatever edges we have already seen? Because when you were saying that check whether the edge is there, if we are storing only the
We are also
previous-
storing adjacency matrix.
We are also storing the other non-tree edges as adjacency lists. Okay.
You can just store the urgency matrix, then it will be just constant. I mean, since we already have mn time methods.
Okay, we can also store the adjacency matrix. Okay. So how to take care of this? How to amortize? So note that the total update time is mn. Okay, let us try to follow this argument now quickly. For each node V, we can potentially store the set of incoming edges from layer I in a separate list, from layer I plus 1 in a separate list, from layer I plus 2 in a separate list, and so on. And we can in constant time check whether this list is non-empty. Okay. Now first look at node V. In constant time, we determine that the incoming list from layer I is non-empty. Hence, we are moving to layer I plus 1. We found an edge u prime, where u prime is in layer I plus 1. We make this part of a tree edge. So we spent some time here, right? But note that, yes, note that what happened? One endpoint of that edge increased its layer. Earlier layer of V was I plus 1, now it becomes I plus 2. Similarly, if you look at, of course we need to fix this entire subtree. Look at this guy W. If in constant time we find a node u prime here whose layer is I plus 1 and has edge here. No, we are keeping this separate list, right? So for each node we are keeping separate lists for each level, say. Either we fix W in constant time because we have found an guy u prime at layer I plus 1, or we have to go down a layer. And the moment we go down a layer and check the edge there, W's level has increased. So this is where the amortization will kick in. We will say each time the algorithm probes an edge, the layer of at least one of its endpoint increases. And the layer of a node cannot go beyond n, right? Then it is unreachable. So that's where this mn time is coming into picture. For each edge m, there will be at most 2n layer increases. Is the high level idea clear?
No.
The-
Don't get anything from that layer. Suppose, so there is still one case there. So that there is a edge from some of V's descendant to V. And then there's we can connect some of these children to the tree.
And that's nice. From the tree to these.
So what happens is that in the new tree, one of these descendant actually becomes its ancestor. So then
You are saying that one of these descendants will become.
Basically, the tree gets located, the child becomes the root of the subtree. And
Okay, good point. Let me now go on to the full algorithm. With this high level intuition in mind, let me just go down to the full algorithm. And before I write down the pseudocode, I just want to give you a pictorial description of what is going on. So, think of this as a picture as to what is going on during an update. Okay. The algorithm will maintain a list of dirty nodes. Okay. And this is layer I plus 1 on layer I plus 2, right? Okay. Let me also give I plus 2. And now the dirty nodes at any given point in time will belong to at most 2 consecutive layers. So look at the minimum V is dirty and L of V is layer of V, okay? And look at this quantity maximum layer, V is dirty, layer of V. Their difference can be at most 1. So right now, suppose the dirty nodes are in layer I plus 1 and I plus 2. Okay.
What is the dirty node which has more than one layer? Belongs to more than one layer.
No, 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 no. The dirty nodes are, each node belongs to one layer. Think of, okay, let me try to give you a better picture. Think of a BFS tree, okay? Just one second. Think of a BFS tree initially, and now suppose I deleted some edge. This guy gets deleted. And the edges that I delete, their layers do not differ by 1, differ by at most 1. So basically the dirty nodes are the ones in this tree structure whose parents are missing. So you have a pointer to its parent, but it does not actually have any incoming edge from its parent. These are the dirty nodes. These are the nodes that we have to fix. Sorry?
Could you repeat the last?
Okay. You start with a BFS structure, then I just delete some edges in such a, if we delete some edges, what will happen? Some nodes will be missing their parents. I mean, some node will have its designated parent, but there is no incoming edge from that parent. That node is dirty because we do not know what its actual distance is. Okay? Now I am saying is that at any intermediate stage of this update algorithm, the dirty nodes will belong to layer I plus 1 and I plus 2. It cannot be the case that there is one dirty node at layer I plus 1, another at I plus 3. This is not going to happen. This is what I said here. Okay?
So when I delete UV, where V, U was the parent of V, now V becomes a dirty.
Yes.
But the descendants of V are not dirty.
No, the descendants of V are currently not dirty.
We still don't know their actual distance, but we don't consider them dirty.
Yes.
Okay.
So the definition is that when a node becomes dirty, you potentially might have to look into all its descendants.
So you why can't I remove some of the random code? Like why?
No, this will be an invariant which will be kept by the algorithm.
Oh.
Again, this is not yet the description of the algorithm. Okay? This is just a little more refined level idea as to what is going on.
So are you claiming that this will hold, or are you saying that we'll ensure that this holds?
Yes, we will ensure that this holds. So note that initially you just delete one edge UV. Then by definition there is just one dirty node V that is missing its parent, and this invariant holds, right? At any intermediate stage we will ensure that there can be multiple dirty nodes, but still this invariant will hold.
But I mean, at every intermediate step, are we storing the BFS tree?
By intermediate stage I mean the intermediate stage of an update. So just one edge deletion has occurred, and then you need to perform an entire amount of computation at an intermediate stage of that computation. Is that clear? I am going to come to the data structure later on, but let's have the picture in mind. So these guys, I am just going to draw them in boxes. These are dirty nodes at layer I plus 1, and here is one dirty node at layer I plus 2. what you do is, since you want to maintain this invariant, just pick a dirty node from layer I. You need to fix this. Check if it has an incoming edge from some other node in layer I. So this is V. Check if no. I drew this picture wrong. Just 1 second. This is layer. If this is layer I plus 1, layer I plus 2. Sorry, let me just make this thing clear. So in layer I am just going to draw the clean nodes and circles, and in layer I plus 1 and the dirty nodes as boxes. So this dirty node is like this. 1, there are some dirty nodes and some clean nodes as well. And in layer I plus 2 again, there are some.
Does the dirty nodes have any relation among themselves?
No, a dirty node can never be a descendant, a child of another dirty node. Okay. So these guys also have their children, and now there are some other dirty nodes. Okay. So now what you do? You just pick a dirty node from layer I plus 1. Let this guy be V. Initially it has its parents here, U, but now this edge has been deleted, that's why it's dirty. Try to find another node U prime such that there is an edge like this. Suppose you find another node U prime like this. Then what you can do, it's done, right? Just make it clean and make U prime its parent. Clear? The trouble is there is no node U prime. Then what you know? You know that V's level has to drop to I plus 2. I mean its distance from source can no longer be I plus 1, it's not possible. So what you then do is, delete this V and decrease its level. So this becomes V. And suppose these were its children, V1, V2, V3. Right? Make these non-tree edges and make V1, V2, V3 as well dirty. Then this invariant is satisfied, right? Can you see the mental picture what is going on? And then you will again do this. I mean, if you cannot find a node, if you cannot find a way to keep this node in layer I plus 1, you will make it dirty. You will keep it as dirty, increment it to layer I plus 2 and make all its children dirty. And this invariant is maintained. Then you will exhaust layer I plus 1. Then you will go to layer I plus 2. And then can you see the intuition that what is happening? That yes, exactly. Exactly the same thing is happening, right? That if you yes, go ahead.
No, this can't go on after n. Right?
Yes, and this cannot go on after n. And the thing is, what will be the data structure? Now I am going to write down the code later on, but let us just figure out the data structure. For each node V, you will just maintain 2 separate lists. One list is the set of edges it gets from the level just above it. And the other list will be the set of remaining edges. So from this guy V,
Set of remaining edges will be just one big list. You won't differentiate between I plus 1 and
no, you don't differentiate between I plus 1. So first,
if we decrement the level, then we have to update that list.
exactly, that's where I am just coming into. So first note that incoming edges to V, they cannot come from level I minus 1 or above. So this is one set of edges and the remaining set of edges are like this. Somewhere below, it can get some edges from its descendant, you don't care, okay? either in constant time you found and you detected that this list is non-empty and you get done with it, V. Otherwise, V dropped, then you need to adjust V's list, right? Because then you need to go through this entire list of remaining edges and decide which of them has parents in layer I plus 1 or not.
More importantly, you need to update other lists.
Sorry?
You need to update other lists.
You
I mean,
move it from there to here.
Yeah, you need to update.
I mean, a vertex in I plus 2.
Okay, so if this guy, sorry, you were just saying that suppose there was an edge here, you need to update this list. Yes, you need to do that.
Okay, that is also a matrix. Sure.
And but the point is that each time you are updating this information, V's level has dropped. And now here is where the amortization kicks in. Okay? So now let us look at the pseudocode. Okay, let me just look at this time. Okay, you should be able to finish it. Just 1 second. Data structure. Now I am just going to write down the entire algorithm. These are the incoming edges from the layer below above it. So this is U in V such that these are the outgoing edges. They are stored as doubly linked lists. This is just a pointer to its parent. And finally, Okay. So this linked list looks as follows. The first nodes in this list are in layer I plus 1, the last nodes are in layer I plus 2. So this is a sorted list. Okay. Then I am not going to write this part, and edge UV is deleted. I am not going to write this part. When an edge UV goes deleted, you just adjust the structures, and in the end what you find is V is now dirt, right? Then you run this while loop. I am not going to write the first few lines. While this list is not empty, take out the first node, remove it, then what you do? Check in minus, right, if there is any parent. If in minus V is not empty, then check any node U in minus, parent of V becomes U, add V to children of U, break, it's over. No, not break. I am going to use this bad notation of go to. It's easier to see what is going on, okay? Go to 1. Otherwise, this guy is empty. Scan through the list in plus of V, while scanning some U in plus V, if you see that LU is equal to LV, then remove U from in plus V, and add u to in minus v. This is how you adjusted this in plus v and in minus v, right? Because now v is going to drop to a larger level. Okay. Then scan through the list out of v. While at some node u which belongs to out of v, what will you do?
If the level of v is level of u minus 1.
Exactly. If level of u is equal to level of v plus 1, so v was at a level above u, and then I am just going to say adjust in minus u and in plus u accordingly. And
You have to take v from in minus 1 and put it into in plus 1.
yes. So what is the situation, right? I mean, v was here, u was here. So then you will adjust this thing, and finally
Increase LV of u, LV of v.
no, there's another thing. Let me continue here. Yes. You go through children. I mean, you need to go through the children's list. You go through this. So what you do? Parent of u now becomes null, and then add u to the end of the dirty list. So this is what happened here. I mean, v is dropping and these guys become dirty to the end of dirty list, and finally set, just remove all these guys from the children of uv list. Finally, increment
No, and add v to the t.
oh, sorry.
So whether we add it after the children or before the children, it shouldn't matter.
No, it doesn't matter. But the thing is that you need to ensure that all these guys are added at the end and not in the beginning, because you need to clean up level I plus 1 first before going to level I plus 2. So this is the complete pseudocode. And now what is the running time? I mean, just look at this while loop, right? I mean, you are just spending some constant time in the beginning to check whether this while loop is empty or not. Other than that, for each iteration, you are just going through this node v, right? For each iteration, the amount of time you are spending is proportional to the total number of incoming edges and outgoing edges from v. It cannot be more than that. I mean, oh, sorry. I take it back. Yes. So either it's constant, so this part is constant, right? And the running time is this part is constant, but if this is happening, then V is no longer dirty in the end.
Why is that constant? I mean, you have to go through a list of ion layers.
No, you can just check if it's empty or not.
Oh, okay.
Okay. So now so this part is constant, but after this V is no longer dirty, and it's never going to be dirty in this while loop. Okay. Otherwise, if it has to remain dirty, then we are scanning through all the edges, incoming and outgoing edges from V, but each of that time, for each such scan, the level of V is increasing. Yes.
When you're scanning through IN plus,
Mm-hmm.
and suppose L of U is not L of V, then for that edge, okay, no, the next step. When I'm scanning through,
Out of V.
out of, what is it, V or U? V. See, okay. For some Y at some U in out of V,
Mm-hmm.
we adjust in minus of U.
Mm-hmm.
So that adjusting, unless you have some auxiliary data structure, some pointer directly to that, you have to scan in minus of U.
Oh, no. That can be easily adjusted.
So you
I
can
mean,
have these scanners from out of V to
yes,
in minus of
yes.
U.
So what he is saying is that given any edge U comma V, can you in constant time find its location in this list, in minus V list and in plus V list? That you can easily do by keeping a pointer from each edge, U comma V.
Then we have to delete that.
Yeah, but that can be adjusted in constant time. Okay? Yes. So first assume that this part, so if you look at this part, starting here, going down here, the total time here is of the order of in degree of V plus out degree of V. Okay. So let us now just, if we want to analyze the total update time over M deletions, let us just analyze the update times for these two parts separately. Okay. For these parts, okay, each time, I mean, you are running into this part of this while loop, you are spending time proportional to the degree, but for each of those edges, one of its endpoint is going down. So by a simple amortization for this part, the total update time is going to be O of m plus n, mn, total time. Okay. So okay, what I said was, just look at that, you want to analyze the total update time for m edge deletions. Just look at the amount of time we are spending executing these instructions in this while loop. If we are executing these instructions corresponding to node V, the amount of time is in degree of V plus out degree of V. But after the end of this instruction, the level of V is going up by 1. So we cannot execute these instructions for V more than n number of times. So the total time spent here is going to be m times n, because for each edge, each time we are doing constant amount of time here, one of its endpoint is going down. Clear? What is the total update time executing these instructions? No, it's also order m of n, for the reason being, after one edge deletion, yes, you can spend O of n time here. Suppose one edge got deleted, and at some point in time you might have n number of dirty nodes and you need to fix them, and each gets clean after this. So if I claim that after
So but this MN is being taken for one edge deletion.
no, this MN is for all M edge deletions.
We're counting the number of times it drops, total number of times a vertex drops from some layer to the bottom.
So for one edge deletion, you take n degree of V plus
Yes.
n degree of V.
Yes.
No,
No, that
it's
is
not
not.
counting.
It's
per edge.
not one edge deletion. We are not counting it here by. Okay, if one edge gets deleted, then how much? Okay, suppose one edge x comma y gets deleted. We run through this entire while loop. For this part, how much time we are spending, I cannot tell you. I cannot guarantee. All I am saying is that just look at the entire sequence of edge deletions. Over that entire sequence, we are not spending mn more than mn time. Is that clear? Why? Because the runtime here is proportional to in degree of v plus out degree of v, but for each of these edges, level of v has increased. Okay.
And for this, you just say that each time a vertex enters dirty, an edge had, I mean, that something had dropped down.
Yes. So for this part, you can argue is that just look at one specific edge deletion in the entire graph, one specific update. After that, you are running this while loop. How much time will you spend in this part here? At most O of n. It's a very conservative estimate, but it cannot go beyond O of n. Why? Because once a node becomes clean here, it's not going to get dirty during the same while loop. During the same update. So again, fix and update x, y, edge graph deleted. Now I am looking at a specific node v, for which this if part was true. Then it got clean at one instance and it will remain clean during that instance. So for the xy update, this part of the while loop is taking at most O of n time. So that's why I am saying that after one edge deletion, this part is taking O of n time in total. So there can be m edge deletions. So the total update time here is also going to be O of mn.
Actually, why
Yes,
is
there is no duty of the automatic.
one calculate is doing that and we're done because
No, in one edge deletion, right, a vertex becomes clean only once. That is the point.
Yes. So there might be multiple vertices for which this is happening.
So for one edge deletion, multiple vertices may become dirty and then finally they can become clean, right?
how can in one institution multiple vertices become okay?
Because there is this cascading effect, right? So you might be running this while loop many times. I do not know how much, but you are not going to spend more than O n time doing this part. Here. So that was the first paper. Okay. Let us stop here. So next class we will talk about strongly connected components and all pairs reachability.
This is the entire JACM paper.
Yes, it was easier to okay, this I should write 30 years old paper. It was the first paper on this topic. Yes.
So the data set is nothing, just these.
Yes.
And now we know better, so the running time is order n times n.
Oh, okay. So the open problem is this. If you just want to maintain reachability trees, I mean reachability information, something better is known, but that is randomized. No deterministic algorithm is known. And for BFS trees, if you want to maintain shortest path information, nothing better than this is known. Yeah.